In this video, we will see about the static rotor resistance control. So this is applicable for slip ring induction motor. This is the slip ring induction motor, which consists of a three-phase winding in its stator, and the rotor terminals or windings are connected at one end in star connection and the other end are brought out and connected to the slip rings. So the brushes will rest on these slip rings, and through that the external rheostats are connected. By varying this rheostat, you can vary the starting torque of the slip ring induction motor. This is not possible in squirrel cage induction motor. Squirrel cage motor starting torque cannot be controlled, or the rotor side of the squirrel cage motor cannot be controlled. So that is the drawback of squirrel cage motor. So in applications where you need to control the rotor side, we can go for slip ring induction motor, though they have many disadvantages, like they are bulky compared to squirrel cage motor, and they are expensive, and they have slip rings and brushes which require frequent maintenance. Let us see how we can control the speed of the slip ring induction motor. By varying the rotor circuit resistance, we can control the speed of the slip ring induction motor. Basically, there are two techniques to achieve this. One is called rotor resistance control. It means that you are controlling the resistance connected in the rotor circuit. Thereby, you are varying the speed of the slip ring induction motor. Another one is called slip power recovery scheme, which is the widely used method. As the name suggests, the slip power is recovered in this scheme. In rotor resistance control, we are wasting the slip power. So which is slip power? This rotor air gap power, part of the rotor air gap power will be converted into mechanical power. Remaining power is called slip power. It will be normally wasted. So instead of wasting this slip power, if you recover this power, it is called slip power recovery scheme. How to recover this power? You can use this power to drive another motor, or you can use this power and return it to supply back. Then we call it as slip power recovery scheme. So either you can give this power, take this power as electrical output, or you can use to drive a motor mechanically. So in both the cases, we call it as slip power recovery scheme. So to achieve this slip power recovery scheme, there are two techniques. One is called static Kramer system. Another one is called static Serbius system. Actually, Kramer system and Serbius system is there. If I use this word static, it means that I am using power electronic converter. Without power electronic converters also, you can achieve slip power recovery scheme. But here, after the invention of power electronics, only static Kramer system and static Serbius system is widely used. Now we will go to the first technique, rotor resistance control. So first we should know what is resistance of rotor. Small r2 represents the rotor resistance, and capital R2 represents the resistance connected externally to the rotor circuit. Now we will see the speed torque characteristics. This characteristics is drawn for different values of rotor resistance. So small r2 represents the original rotor resistance, which is shown in green color, and the starting torque is Ch.21. Now if I am adding some external resistance, the speed torque characteristics, the shape will not change, but you can see that the starting torque has increased as you increase the resistance. So for R2 dash, the resistance starting torque has increased. For R2 double dash, again starting torque has increased. So by controlling the R2, we can do two things. You can change the starting torque as well as starting current will also change. But you have to note down here that you see the green color, that is without any external resistance, your maximum torque occurs at one speed. If I add external resistance, the maximum torque occurs at a lower speed. So the slip at which maximum torque occurs is decided by the external resistance. However, the maximum torque magnitude will not change, or it is independent of rotor resistance. Next we will see the speed current characteristics. Here we can see that the curve is drawn between speed and the stator current for different values of rotor resistance. Now small r2 represents the rotor resistance without any external resistance. So in this case the stator current is high. If I add some external resistance, stator current is getting reduced. So by increasing the external resistance, stator current get reduced. We can observe from the speed torque and speed current characteristics that by increasing the rotor resistance, we can get higher starting torque, starting current will be reduced, and the speed at which maximum torque occurs gets reduced. But maximum torque magnitude remains the same irrespective of the value of external resistance. Let us see the advantages of this method first. So there is no inrush starting current because we are able to control the starting current. You can get higher starting torque, high power factor, and wide range of speed control is also possible. If we see the disadvantages, the efficiency will be low at low speeds and wide speed change for load variations, and if the rotor resistance are not equal, there will be unbalance in the voltage and current. Next we will see the applications. So this method is preferred where speed drop is required only for a short time. For example, you can take overhead cranes which is used for loading and unloading of machines or products. So here this type of speed control is very useful. Next we will see about the static rotor resistance control. As I told earlier, if we use this word static, it means that we are using power electronic converters in the circuit. So in this static rotor resistance control, we are using power electronic converters or power electronic switches to control the rotor resistance. So earlier we were manually changing the rotor resistance. This part can be replaced by a chopper resistance and a diode bridge rectifier. So you see here resistance is here, single resistance is here, which is connected across a switch, which we call it as a chopper. So a switch and resistance will be in parallel. You turn on and off the switch, so the resistance seen by the rotor circuit will change. So if you see here, this stator we are giving 3-phase supply. In rotor, here in rotor circuit, this will be at slip frequency, that is the AC. So you want to control the switch, so you need DC output. So this diode bridge rectifier will convert the slip power, because that frequency is different. That slip power will be converted into DC here. This inductor will filter out the ripples in the diode bridge rectifier, and after this filtered output we are connecting a resistor in parallel with the switch. So by turning on and off this switch, the resistance seen by the rotor circuit will change. So the diode bridge rectifier converts AC to DC, and this inductor is used to smoothen the current, DC link current, and the switch controls the effective value of the rotor resistance. Let us see how it works. So when the switch is on, means it is a short. When you short a resistance, what will happen? Current will not flow through the resistor. Instead, it will flow only in this path. So if it is shorted, what happens to the voltage here? VD. It is a short means voltage will be 0. So this voltage and this voltage is going to be 0. Under off condition, so this switch is off. So the current flows through the resistor. So resistor is connected in the circuit. So during on period of this switch, the resistance is not connected, and during off period the resistance is included in the rotor circuit, and this is the VD, the voltage here. So when it is on, voltage is 0. When it is off, there will be some voltage which will be equal to ID into R. Here it is ID and this is R. So V is equal to IR, so it is equal to ID into R. What is duty cycle? Alpha is given by on time divided by total time period. So what will be 1 minus alpha? T off divided by T. So the effective rotor resistance is equal to R into, you see here R is connected only during off time. So I am writing R into T off divided by T. So what is T off by T? It is 1 minus alpha. So RE, I can write it as R into 1 minus alpha. Now we have included a chopper or power electronic converter into the rotor circuit. So the equivalent circuit will change when you use power electronic converters in the rotor side. So let us see how this equivalent circuit is getting changed because of this connections. So stator side remains same, only rotor side we have connected. So till this part the equivalent circuit remains same. After that we are connecting a diode bridge rectifier, then an inductor and a resistor is connected. You see here it is RE, not R. It is the effective resistance RE. So this part is connected extra now. Now let us neglect the stator and rotor leakage impedance when compared to this inductor LD. So this is neglected and we are focusing on this part. Here you have 1 turns ratio which represents the number of turns in the rotor and stator. So A is given by N2 by N1. So we have to derive the torque equation for this one. For that, first of all we will take the equivalent circuit which we have already studied in electrical machines. For induction motor you might have studied how to draw the equivalent circuit. Same procedure. I have given all the equations which are necessary for deriving the torque equation. So the stator voltage per phase is V1. So this is the stator voltage. So what is the rotor voltage? Here. So this before the transformer primary side you have V1. This side you have rotor side. So rotor EMF is equal to S times E2. Now you have a turns ratio here. So let us consider this, the stator voltage when you refer to the rotor circuit. You have to multiply by the turns ratio. So N2 by N1 into S times V1. So that gives N2 by N1, already we have seen it is taken as A. So A is equal to N2 by N1. So I can write it as A into S into V1, which is equal to SE2. So this voltage, rotor voltage, is given as input for the diode bridge rectifier. Now we will see about the diode bridge rectifier. So we have already seen what is the voltage here. Now after diode bridge rectifier, what happens? So the rectifier output voltage VD is given by, so this is a 3-phase diode bridge rectifier. So the formula, output voltage formula is 3 root 3 VPM by pi, where VPM is nothing but root 2 times VRMS. That is given by VRMS. We have already derived what is the RMS value. So root 2 into ASV1. So VD is equal to, you put all these things, you will get 2.339 SAV1. So this is the VD formula. So you have to remember what is the voltage here. Now the rectifier output power, you can write it as VD into ID. Power is VD into ID. What is slip power? So whatever the rotor power we have is 3S into PG. So both are same if there are no losses in the diode bridge rectifier. That is, the input power is equal to output power if we assume that there are no loss in the diode bridge rectifier. So let us equate it. So you equate it and you find what is the air gap power PG. That is equal to VD ID divided by 3S. So PG we have calculated. Let us calculate the per phase developed power. That is, the mechanical power is equal to 1 minus S times PG. So 1 minus S times PG value is substituted. So here we know PM is equal to omega into T. So let us substitute, instead of omega T, instead of PM, substitute omega into T to 1 minus VDID by 3S. So instead of omega M, you can write it as 1 minus times omega S, so that we can simplify it and find the torque equation. Next we will find the DC current from the torque equation which we have derived. So ID is equal to this one. Let us substitute, instead of VD, this equation. So 2.339 SAV1. So you simplify it, you are getting the DC current equation. Now we will see what happens if we apply the load. Let us say the load torque is equal to TL, and that will be, load torque will be equal to 3 times this motor torque, because it is a 3-phase machine. We have taken TL is equal to 3 TM. So ID is equal to, you instead of TM you put TL by 3. So 3 will get cancelled and you will get the ID equation. So you can see here ID is directly proportional to synchronous speed, load torque as well as stator voltage. So it doesn't depend upon the motor speed. So we can see that this current through the inductor is independent of the motor speed. Now we will calculate the motor speed. So if assume that this inductor is ideal, so what is this VD? That is equal to ID into RE. What is RE? R into 1 minus alpha. So I am writing VD is equal to ID into R into 1 minus alpha. So what is VD? We have already derived it. That is equal to ID into R to 1 minus alpha. So from this we can calculate what is the slip. Now we will calculate the motor speed. Omega m is equal to 1 minus s into omega s. You substitute this slip value here and you will get the speed equation. So you can see here, if I increase this load torque, this is 1 minus load. So if I increase this one, the motor speed will decrease. So if the alpha is fixed, as you increase the load torque, speed will decrease. Next we will see the closed loop control of the static rotor resistance control. You have a power electronic switch which needs to be turned on and off to control the resistance seen by the rotor circuit. So how to turn on this IGBT means, if you give a gate pulse it will turn on, and if you remove the gate pulse it will turn off. So how to control this gate on period of the switch, that is decided by the controller circuit. So this part is the power circuit and this is the control circuit. You can remember always there will be two controls in any drive system. This is the basic drive system, that is inner current loop will be there and outer speed loop will be there. So first you have to measure the speed and set a reference which will give you a error, which can be given to a P controller, PI, PID or fuzzy or whatever controller you want, you can give it. From that a reference will be set, that is called the current reference, and here you will get the measure the actual current using some sensor. So from this error will be calculated. Again you have to give it to any other controller like PI or PID, any controller you can give, which will generate the firing pulse for this IGBT, gate pulse for this IGBT. So by changing the resistance, the speed torque characteristics will change, or we can control the speed by changing the on time of this chopper. So the points to remember here are, the speed control can be achieved by varying the rotor circuit resistance. In static rotor resistance control, we can use a chopper resistance and a diode bridge rectifier. By increasing the rotor resistance, we can achieve higher starting torque, reduce starting current, and the speed decreases, or the speed at which maximum torque occurs decreases. But there are some disadvantages, like in this method the slip power is wasted in the external resistance, and because of that we are getting lower efficiency. If you like the video, please subscribe to Read Electric Vehicle channel. Thank you.